Okay, so we'll go ahead and kick off the recording for our Go meetup for January the 3rd, 2023. We've already done a little bit of in-house chat, but I want to record this one for posterity, so I'm going to hand it off to Derek Perkins to do a lightning talk for us.
You need to join the Google Meet to present.
Yep. We should have had. Join that.
Java, huh?
It's a language.
Yeah, I'm not going to be banned.
Oh, he's wise to my tricks.
Where do I get the link?
Meetup.com.
.com, what?
I can also send it to you. So I should have had it prepared before I started the recording.
I just pinged the link to you.
Thank you.
I know Mariah loves editing, so
I do it all on YouTube now. It's fine.
really, they have a built-in editor now?
They've had a built-in editor for 2 years.
I haven't uploaded a video for 15 years now.
All I do is I say chop beginning, chop end. I'm not doing anything complicated.
Perfect.
If you have a server at home, then you can.
Seriously.
Okay.
Oh, there's money.
I just muted myself. No. Stop looking.
Ah.
Look at my
Where is-
jokes.
Wait, so do you use this library at work?
Yeah, we launched it in a product 2 weeks ago.
Yay.
Always, my favorite talk for the ones that people actually use. So you've already checking the boxes.
There's no sound that I can output to. I guess I'm not plugged into anything.
Platform we use.
I think you can share. If you share a tab, you can share sound from a tab.
Sharing a tab.
You should keep anything with the browser. That's about it. If you play it loud enough, it'll.
You can live this.
We'll see. All right. Caching, a sometimes necessary evil. But less often than most people think. So to start off, founder of Nozzle, we do SEO analytics. Like to say we store Google on Google inside of BigQuery, and we help companies keep track of where they rank on Google, what the competitors are doing, all kinds of data. So data is important to us. So databases, they're a big deal. Is it running slow? What's the first thing that people think to do? Sprinkle a little Redis on it.
Woo! Oh, we're gonna have to set some terms right up front. Redis?
Sorry, it's a long running joke. There was Joe worked with a guy who called it Redis and wouldn't let Joe like fix indexes on the database. So it is henceforth been Redis. So sprinkle a little Redis on it. So I found this benchmark. It's not a,
I don't think your slides are updating.
you didn't see my, oh.
Oh. I mean, I saw it earlier, but I was told not to look. You obviously should have cached your slides before you.
Maybe the slides got automatically.
It's either the answer or the problem. One of the two, for sure.
DNS too.
Yeah, or DNS.
DNS has a cache.
It does.
Show my GIF.
Maybe.
Your GIF?
Mm.
Yeah.
There it is. Oh, there you
I'll
go.
fight you right now. I'm just kidding.
Sprinkle a little Redis on it.
There we go.
So when do I need to stop editing the?
Okay, so I found a benchmark. It's not the world's greatest benchmark, but it proved my point and served my purposes. So believe it or not, databases are actually really good at key value lookup. It's not that Redis is this magical. It's the only thing that said, oh, what if we return values out of memory? Your database does it really well. MySQL has buffer pools. I don't know what the equivalent is called in Postgres, right? But hot data and the pages that they're on are stored in memory. Everything's served out of it. So this benchmark shows just as you increase the number of requests, what's the key value lookup time? This is MySQL and versus MySQL with a Redis lookup on cache miss. And, you know, here up till you get to 1 million requests, MySQL is faster.
Per second?
I think this is total requests. Again, it's not a,
I only have questions.
but in the general case, it's going to be super fast at key value lookups. And
Inconceivable! You keep using the word. I do not think it means what you think it means.
Pronounced Redis.
right, so caching doesn't always mean what you think it means, because the best cache is no cache.
Oh, there we go. Okay.
Right, you can add indexes, increase the resources available to your database, right? If you're gonna take the time to deploy a Redis cluster, you're gonna work on HA, right? It's gonna take lots of its own resources, not to mention maintenance. And if you take the same amount of resources you are going to apply to Redis, your database will probably serve Redis plus your database. And then you don't have to worry about stale data. If you're still having some problems, spin up some read replicas. You probably get that for free, and you're going to have some of them running anyway for HA or hot failover. And then you do have some consistency to deal with, but again, it's free. So try not to cache. Sometimes you have small data. You don't need a big external cache. So this is a client we have for ChargeBee. I have many words for ChargeBee, but I will not say them here. But they have a pretty low rate limit on their API, and most of the objects that we access are very slow moving, not quite immutable, but nearly. So we just use a sync.map on the client and call it a day.
Stop booing. There's nothing wrong with it. There are dozens of us. Dozens!
I bet this is a great presentation on your screen.
How's
So
the rest
just
of
one-
development, right, with the
It sounded like.
the never
Never
news.
news.
Never knew.
It is the never news.
Dozens of us.
I don't know what's going on.
So your
It's
data,
probably better for like
dozens of us.
There it is.
So in our case, we then, sync.map wasn't quite everything that we needed. So we said, hey, let's put on a per pod cache. Again, this keeps us from having to spin up extra infrastructure, and we can still serve hot reads straight out of memory. Ristretto is great for that, built a dgraph, pretty awesome. They've got a really good set of articles comparing it to the other in-memory caches, Go memory caches that they compared it against.
Do you run that as a sidecar or is that a second process you run? You compile it, your binary.
It's not a second process at all. It's just like a map. So
It's a
it's
library.
got to get input and
But, so you pull in a package to your Go service and you run it. How do they discover each other? Like,
no, it's just a,
oh, it's a per, I'm sorry.
it's just an in-process Go function.
I see. Okay,
That's
it's
just
just,
calling get input.
it's not
That's it.
distributed. It's just like a
Yeah,
permanent sync map
Yep.
cache. Okay, sorry. Gotcha.
So we ran this, we gave it 30, 50 meg, something like that, you know, per pod. And that worked great for some of our hot processes. But the problem is, right, load balancing as things we have a lot of pipelines that at every step along the way needs to request kind of the same data. For us, it's a keyword. And there's no guarantee that it's going to hit the same server that has that already preloaded in cache. And so we said, all right, what do we do now to keep speeding that up? So the OG from Mr. Brad Fitz, that some of us in here know personally and are best friends.
Does code reviews for him.
Yeah.
They highlight.
All right, so group cache serves to fill that need where you can take this in-memory map, turn it into a distributed cache. And, you know, in here in the description, it's intended as a replacement for a pool of memcached nodes in many cases. He wrote memcached, he knows what he's talking about. So it's got lots of cool things about it, shards by key, but it doesn't require a separate set of servers. It's got some cool cache filling mechanisms, where if you do have a thundering herd, the first one that gets it makes the request and then reserves the same response out everywhere. But it also doesn't support versioned values, which means you basically can only store immutable data in it. There's no evictions. But you can also do this automatic mirroring. So rather than being strictly one shard contains one key, hot items get mirrored out into every node so that everything can be a local cache hit for those hot items. So again, it's shared. It's again great that there's no separate deployment. And another interesting thing that you have here is cache isolation. So if you've got Redis, it's easy to get some contention between different services that are taking more or less resources, CPU, RAM. But here you have per group or cluster of processes, they have access to their own RAM and nothing else is going to evict it. Also, group cache is not trivial Kubernetes setup. Mailgun has forked it and added some eviction and other stuff, but it still doesn't do all the things that we're hoping for. So introducing Ulrich. It's very similar in a lot of ways to group cache. It's a distributed in-memory store. It's embedded. There's no sidecars. It's just in memory, and it just works out of the box. So there was just a recent release that was a complete overhaul that switched it to use the Redis protocol so that you can actually run it as a Redis replacement. I don't know why I would do that, but
Got it. Redis instrumented a bunch of code, I guess.
yeah.
If you have a SIP proxy that only supports Redis, but you want the fast changing data between servers that Redis doesn't offer, that would be awesome.
So
I know, I see you. I was over here. Huh.
compatibility, lots of cool stuff. It also provides beyond just the cache. We're not using any of this, but hub sub operations, you can do distributed locks that are cool, different evictions. It's not consistent necessarily, but you can tune different options for quorum reads and writes that can get it to almost consistent, strongly consistent. So cool stuff. And
This is pre 1.0.
yes,
Okay, that's fine. That's not a problem. Just good explanation of where they're at.
That in.
Yeah. I do that.
0.5 for whatever that means.
It's not 1.0. That's what that means. That's.
So getting started. So I'm going to share, this is a mixture of our wrapper around Ulrich and the Ulrich initialization code itself. So this is creating a cache. So this is, there's a Kubernetes discovery mechanism. It's a pluggable discovery, so you could use whatever you wanted. There's some defaults in the config for LAN. Under the hood, it's using a HashiCorp member list that powers a lot of distributed applications in Go. And that passed through into that.
Populate the member list. Like you said, it works out of the box. I have to imagine it's got some sort of.
I will show you in just a second.
Okay.
It's this
Service
states
discovery.
discovery mechanism. So then we actually create it, then we start it in a Go routine. We're going to interact with the local cache through this embedded client that's created here at the bottom. But it's still in our local memory if we get a cache hit. We wait for it to set up and then just some, listen for shutdown so that it can gracefully leave. It'll notify other members of the cluster that it's leaving. And there are some settings to let you redistribute keys or repair reads that we're not using at the moment. So Kubernetes Service Discovery. It's a pretty simple mechanism. So we're setting up a Kubernetes client here, and that's it. For us, we have one service per namespace, so we don't need a lot of config on this. And there's a lot of hooks that you can implement for Ulrich, but we only need this one. Discover peers that just says list all the pods in the namespace. You can do label selectors or anything else if you needed to. And then this pod addresses, I copied out of HashiCorp Go Discover that just finds running pods that are in a good state. So pretty simple. And it just
Does
works.
it have the service discovery interface that you implemented? Is that what that was?
Yeah. So
But it does depend on client. I can't imagine they have depending on client Go. You just wrote it.
I wrote the client Go.
Okay.
Yeah, the imported client Go to increase the binary size by like 200 megs.
That's exact, no, it really does. Yeah. And that's why I would have been shocked if they built it in the language.
So just up there at the top, that's where I'm asserting that we're implementing the service discovery.
Okay.
So you can use Kubernetes or
Anything.
Get a list of things. Okay. DNS.
So then the core thing that we're using is a DMAP, distributed map. And we're wrapping it in our limited proxy because we don't need access to all the things and it's convenient for all the reasons. So here we're initializing it. We're setting eviction policies, the max memory we're going to use. There's some settings that we're not setting, like max keys, and I can't remember all the things, TTLs. We do have this max idle duration set up. We're also making sure that we don't accidentally over allocate. So we make sure that between all of the DMAPs that you end up setting. So just like any map, it's not indexed. So essentially any index key value lookup is going to be a separate DMAP and takes its own memory. So we're just saying, let's make sure that each pod doesn't have 500 because this is multiplied per pod. So 10 pods and now you've got 5 gigs of RAM allocated to it. We're talking about the JVM and memory before. So running all Go like we do, we have a lot of memory available since we don't have 1,000 JVMs running. And so we have overhead to use a lot of RAM where we want to. So gets pretty straightforward. This underlying get in here is just a get. We are also wrapping a scan around it that'll work kind of like a database scan where we're actually checking for protos because that's our common use case is storing proto responses. And Ulrich itself, the scan will work on basically every primitive in Go plus time and duration or anything that that implements the Marshall binary interface in the standard library, which Proto does not do by default. So we may end up implementing that or just generating it ourselves and having to use Proto encode, Marshall and unmarshall like we have here. But for now, this wrapper does it and it's just fine. That is an interesting, as you move from just your local sync map or even some of the other like Ristretto, since it has to now be serialized, It's not just as easy as, oh, I take an any and you get your any back and type assert it. It does actually have to go through the serialization. Or if you don't have a proto, if it is a, simpler object, you can just scan it and it scans it in for you. We're swallowing the errors because there haven't been that many. And
That you know of.
by swallowing, we are reporting them internally, as you can see.
Yeah.
But we're not making the developer deal with it, because if the cache is down, that's not really their fault.
Plug for our online viewers, E is amazing.
What?
Plug for our online viewers, E is amazing.
Yeah.
It's open source.
Woo-hoo. That was my last lightning talk. Puts are even easier. Same story. We're checking to see if it's proto, and then we're marshaling it. Otherwise, we're just putting. So those are all single gets and puts. You can also do pipelining, same as you can pipeline on a normal Redis instance. And this is just a snippet of code from inside the Ulrich library itself. It goes through and it understands this part ID that you see down here in the map. It knows which keys live on which shards. And so it combines all those together and sends one batch network request per shard to do your gets and puts and whatever, which is convenient. So how well did it actually work for us? So this is the underlying latency of the service. You can see as load picked up, so that the latency before peaking at 260 milliseconds here in this slide. And then afterwards, much better, 90% faster on P99, and even P50 is down significantly. Surprised me.
You solved it on 1214.
So those are low load.
You almost could miss the improvement because it
Go back far enough.
scale, right? Like you drop an order.
Those numbers on the left have changed.
It almost looks like it's worse. And you're like, oh, no, wait, it just gets.
Oh yeah, when it first popped up, I didn't get it. Then I was like, oh yeah, scale is different
Yeah. Cool. So 10 times faster
in order.
and much more consistent. Less spiky. So that was the gRPC service itself. This is our hottest service that is calling it. That was the primary reason we did this in the first place, that it's doing lots of things, but you can see latency on that service dropped here when we deployed it. There was you can see in this gradual decline as the cache is filling. There is no serialization to disk for a quick reload of whatever cache lived in memory before. So that is a downside to if it's a service you're redeploying constantly, you're going to have some high latencies on redeploy. I believe there's some work going into slowing down rollouts and having keys moved in a more reliable manner. But for now, it rolled out fast, and for us, a little spike in P99 isn't a big deal. Here's the total. So these are all in that same service. So just this one gRPC call that's only called once or a couple of times during the life of each of these requests. This went up 25, 30%. And then this is our biggest thing that we accomplished. So this is the total messages in the queue processed throughout the day. And we had days like on 12/18 where we didn't even quite complete by the end of the day. So you can, again, see that we almost doubled how fast that's running.
For the peanut gallery watching online, it's worth asking yourself, do you have graphs like this to know how your stuff is behaving?
You need it.
That's what really makes this journey of yours magical, is you can see the effects and you know what it was before and after, and you know what it's affecting.
Yeah, good job. Well, so a little bit of a caveat. What's not shown here was another service. So the first service we used just was single get and put. We have another service that on average requests about 100 keys. And we started using the pipeline and it had some bugs in it. And we saw the opposite direction effect and a few orders of magnitude worse.
This was my magic bullet.
But
Roll it back, roll it back.
so we rolled it back. There's 4 or 5 PRs that I've put in. Not all of them bugs, some of them just allocation fixes
To
and
Ulrich.
performance to Ulrich itself.
Cool. Nice.
So pipeline will be awesome once.
It's pretty 1.0, it's fine.
So it's also important to watch those in case it doesn't improve.
Good man.
They're single-handedly did the 0.5 release probably.
I did not. I've had my eye on this project for probably a year and a half, 2 years. And finally convinced myself that it was important enough to roll out and not just well, this just feels super fun to do. But it was surprisingly fast to do. The memberless stuff just works. That Kubernetes service discovery just works, and it was great. So Tencent and IBM Cloud are 2 of the bigger companies using this. I don't exactly know to what extent, but they're logos, so great logos. And
IBM Cloud exists.
That's
That's
it.
the thing I learned.
Things I learned today, huh?
Is the friendly face because it's just Twitter in general, or because you didn't get Derek Perkins?
yeah, it's because of that underscore, very bitter. about
Okay, I
it.
wasn't sure.
Have a less popular name, dude.
I also appreciate that you start your presentation with, you don't need this probably at all. But let me tell you how cool it is. If you do need it, it's really great.
Let me make
So,
you jealous that we did it.
That we need it.
Any questions?
Do it again.
Yeah, for sure. Again, it didn't take that long to figure out. It just worked. And there's something. Oh, if you're interested in good, clean Go code, I've been very impressed with the quality of code in it. For something that is, a hairy distributed system, the code is very easy to get into. I kind of went in looking, saying, oh my gosh, this pipeline is probably going to be terrible to debug and look at when I don't know the whole underlying system, but the abstractions are in the right place. It's well formatted. It's well thought out. It's one of the best Go code bases that I've encountered. So if you're interested in just seeing how a distributed system is set up and run, highly recommend just looking at the code for that.
That's worth putting in the Golang channel in Slack as well.
Will do. Well, thanks, everybody.
Anything else want to do, let me talk on the record?
On the record ever.
No? Okay. Thank you. We'll close that. We'll do some more stuff in here and stop.